plan interpretation. I think yes, you can share. Perfect. Please go on.
Thank you, Giorgio. Good morning. I will present a work in which we tried to handle, in this case, floor plan documents, collections of floor plan documents, trying to go beyond simple recognition of components or of the overall kind of floor plan by using an actual interpretation of its content. After introducing and motivating this research, I will discuss and present our approach to floor plan interpretation and its specific steps, including, among others, furniture identification, room recognition, and then the actual plan interpretation. I have to stress the fact that this is a prototype aimed at showing that it is feasible and what it is feasible concerning specifically the use of reasoning techniques in the interpretation step. So the preliminary steps like furniture identification or room recognition are not to be considered as the state-of-the-art techniques for carrying out those steps, but just something that could help us in reaching the final step, which was our real focus. Then I will conclude and outline some future work issues. So we think that a true understanding of the logical and semantic structure of documents is very important, both for really understanding the content of single documents, but also to enable higher level tasks on document collections. For instance, retrieval, browsing, question answering, and a number of semantic activities that can be carried out on collections of documents to grasp a high level understanding also of the overall content of a repository. In this kind of perspective, we think that technical documents are particularly interesting and challenging. So actually, I'm in the text processing session, but I'm an outlier. I'm there by contraposition because I'm trying to use everything but text in document interpretation. And in this case, technical documents are interesting because their content, their meaning is hidden and implicit in the graphics. And while sometimes vector graphics are used, especially for creating the diagrams, actually what is really available is often a raster version of the documents, which adds challenges to the task because in this case we don't only lack metadata which can be added to vector graphics, but we even lack the real structures of the graphics and have to recover it by preprocessing techniques. So our aim is to improve the usefulness, to prove, sorry, the usefulness of formal reasoning approaches in technical documents understanding. This falls in the general area of document image analysis and understanding. And here we found that most approaches work only at the syntactic level, and at most they just scratch the surface of the real semantic level. So they typically label simple or aggregate components of the documents of the whole documents. But we think that full support to final users might include a help to interpreting the document and also to carry out additional inferences on those documents. I will provide some examples in a few slides. In particular, we focused on floor plan as a kind of technical documents because floor plans are much more widespread than other kinds of documents, and they have an interesting feature that they may start and interest and so require interpretations both by highly skilled technical people, but they can be interpreted also by the layman, let's say by everyday people, for instance, trying to guess how their house might be organized. So, as I said, well, it's not just a proof of concept because we actually implemented the prototype, but we just focused on proving what could be done. And so we also used quick and dirty techniques in our pipeline, not aimed at ensuring the best results. This is a very simple example of a clinic floor plan, which I will use in the end, but just to give an idea, in the end to show, to discuss a little bit the results. So our processing pipeline consists of the following steps. A low-level image preprocessing to just enhance the image, then walls identification, floor plan segmentation to identify relevant objects, non-structural objects, and then symbol recognition to label them according to their class, usually a furniture type of class. And then we may describe what we have found in these steps using symbolic descriptions, especially first order logic ones, because relationships are extremely important in understanding floor plans. And then we will apply reasoning at the moment just to understand the kind of floor plan, but in general also to carry out more advanced kind of inferences and to draw more interesting conclusions. Preprocessing basically consists of two steps. Binarization, because the relevant information in floor plans is basically in the structure. So we may safely scale down to black and white images. In particular, we use the traditional OTSU method for this, for automatic thresholding. And edge enhancement, when we use a combination of OTSU and Sobel's approaches to obtain a negative copy of the image to mix again with the original image and try and enhance the edges, which are those revealing the structural and non-structural components in the floor plan. Concerning walls removal, we assume that walls are continuous, thick and solid black lines used to partition the space, and they are obviously the largest connected components in the floor plan. So we first extract all candidate components, which are those having a size above average, and then since some furniture objects might be attached to the walls and we want to only get the walls, we erode and delete twice the result and then subtract the walls from the original image. What I have to say here is that while other approaches use walls, wall detection to identify the spaces, the locations, the rooms in the floor plan, we don't just use walls, but walls are just one of the components which allow and help us to identify locations and rooms, because we may identify several locations within one room based on the spatial organization of furniture. Concerning image segmentation, we obtain it by region growing. We use a four-connected approach to region growing, and we use it because it's less dependent on image size and does not require a threshold, because floor plans coming from different sources may have different resolution, size, and so on. Basically, the three phases we use for our black and white binarized images are background expansion, by which we, starting from a background pixel, find the most part of the background. Then in what is not included in the background, we iteratively select a foreground pixel, expand it, and consider the result as an object. For this object, we compute the bounding box and copy it into a new image by also removing all objects whose bounding box is smaller than 3 × 3 pixels as a form of very simple noise reduction. Once we have these objects, we have to classify them. Our symbol recognition, we adopt a symbol recognition approach. So we see object recognition as object classification, and we adopted a standard neural network approach for this. So we extract feature vectors from each object image, which is a color image if we extract it from the original document. We resize it so as to normalize it to 100 times 100 pixels size. We center the image with respect to every dimension, to both dimensions, partition it into 16 regions, 25 by 25, and for each of the 25 columns and for each of the 25 rows, we compute the average main channel value, red, green, and blue, and mix them by this formula. So basically, we get a decimal number where the first three digits concern the average red, the next the green, and finally the last the blue. Finally, we just concatenate these 16 vectors of 50 elements, obtaining an input vector of 800 values, which is our input feature vector, while as a output feature vector representing the class of each object in the training set, we use a one-hot vector sized 200, which is the number of classes to be recognized. Very quickly, our artificial neural network is a multi-layer perception with 3 layers. The input and output layers were just the same as the examples. And the hidden layer included 500 neurons using a sigmoid function. The output values of neurons were in the 0-1 range. And so we had to, of course, normalize the feature vectors for this. Our training consisted of 500 epochs. Here you may find some details, but in the paper you may find more. What's important is that we also allow our network to avoid recognizing objects. So we recognize an object only if its output neuron has value greater than 0.9. We trained this artificial neural network on 188 images, which are 47 items, furniture items drawn from our dataset, each represented in 4 orientations. This is about 10% of our dataset of furniture objects, and applied to the remaining 90% furniture objects, we obtain 96% correct labels. To improve the result of the next phases, which are the most interesting to us, we fixed manually wrong classifications. Of course, the good results are due to the fact that the training and test set were very stable as a distribution taken from the very same set of objects. Okay, as to floor plan interpretation, as said, our goal is understanding the type of building based only on graphical information, so shape, furniture objects, types, and organization, without considering possible text in the floor plan expressing explicitly the kind of room or whatever. So our strategy consists of 2 steps. The first step focuses on locations, so identifying locations starting from the kind, number, and organization of furniture objects and of the previously detected walls, and then identifying combinations of these locations that may identify a kind of building. In particular, in this experiment, we focused on living room, on 5 kinds of floor plans. And for instance, a living room, a kitchen, a bathroom, and a bedroom in a given disposition might identify an apartment. As regards our first order logic representation, we focused on 3 kinds of concepts in our conceptualization. The physical objects, which are all the structural and non-structural furniture objects recognized in the previous steps, locations, meaningful spaces or rooms in the floor plan, and the whole plan. We think this is a quite general conceptualization which can satisfactorily express a number of possible situations and can be easily extended for more complex floor plans or objectives. These are the predicates we used for describing the basic information coming from preprocessing. So each object has a unique identifier, and we described its type of furniture, its direction in case it has an orientation, the full bounding box and the center of the bounding box, plus a parameter we provide to the next steps, which is the maximum distance, which may be provided manually or automatically computed from the floor plan, the maximum distance by which objects can be considered as belonging, adjacent objects can be considered as belonging to the same location. This is, of course, crucial. Based on facts built on these predicates, we use 75 rules divided in different groups and, of course, at lower or higher level of abstraction to carry out basically our understanding task. So understand when two objects might belong to the same locations, infer mutual positions of objects starting from their coordinates, describe spatial organizations and aggregates of objects, describe possible locations and possible kinds of plans. Here we focused for this experiment on 5 kinds of plans, which are apartments, classrooms, clinics, restaurants, and cinemas. So the interesting part of this approach is that while in this experiment we manually provided for testing purposes the rules may be also learned automatically, and this will significantly increase the flexibility of our approach. Our dataset consisted of 30 floor plans, and our approach was able to correctly recognize 26 of them. For the other 4, we understood that some of our rules were overly specific because they were not recognized due to some missing furniture objects or dispositions of the objects. This is the output, actually the first step of the output. Under the floor plan, we see which are a list of the recognized environments and a list of the physical objects for which we recognized those environments. So for instance, we recognized 3 bathrooms, patient bathrooms in the clinic, each of them thanks to those 3 objects, which are toilet, shower, and sink for 3 times, a waiting room, 3 patient rooms, and so on. So by clicking on these rows, we may have a human understandable explanation of this recognition. So I think this is a clinic because I found these and these and these locations, and these and these and these locations were identified based on these reasoning considerations. So we think that these results are promising to the general goal of understanding and the interpretation of floor plans and in general technical documents. We would like to carry out future work for improving and refining the technique, stepping from a demonstrator to a more reliable system, and add information for carrying out additional interpretations, not just the kind of floor plan. For instance, given a floor plan of a building, of an institutional building, understanding whether it is compliant or not, or what to do to make it compliant if it is not compliant to norms and regulations about, for instance, safety of the people in this period, for checking whether it is COVID compliant, and so on and so forth. Thank you for listening.
Thank you very much, Stefano. I think we have 1 minute for questions, if you have a quick one. Okay, I have a very quick one about the training of your neural network. If I'm not wrong, you said that you had a little bit less than 200 images rotated northwest.
Yes, 100,
exactly.
actually 47 images, and then 188 images because each image was rotated 4 times.
And do you think using some kind of, let's say, sort of standard procedure for training neural networks, like stretching or changing a little bit the shape in order to have more data, would help in that case? Or is it not just reasonable in the sense that floor plans have that structure, so unless you have a very bad scan or whatever?
Of course, this was a quick and dirty technique because we just worked on our data set of 30 floor plans. And so our objective was moving quickly and efficiently towards the latest step. So, yes, for sure, we may improve general learning in case we aim at applying this strategy to real world tasks. We have to identify which kind of modifications to apply. For instance, stretching, I'm not sure, since object representations in floor plan is very standard. Well, you have different standards, but each of them has a very strict representation. I'm not sure that stretching is useful specifically, but for sure other additional kinds of modification other than just rotation will be definitely needed for learning, given especially the importance of object recognition to the later step.
Yes. Okay. Thank you very much.